Deep within the unilluminated expanses of the interstellar medium, a solitary celestial entity drifted in absolute darkness for an immense duration of time. Astrophysicists estimate that this wanderer traversed the cold void of the Milky Way galaxy for a time span stretching between 11 billion and 12 billion years. To place this metric into a comprehensible astronomical framework, this object was already forging its path through the cosmos long before the gravitational collapse of our solar nebula occurred, and long before Earth coalesced into a solid planetary body. Throughout its multi-billion-year journey, this relic of an ancient epoch bypassed millions of distinct star systems, remaining completely undetected, untouched, and uninfluenced by external stellar radiation. It existed as a silent witness to the early structural evolution of the galaxy, carrying pristine chemical compounds preserved from an era that succeeded the Big Bang by only a small cosmic margin. The trajectory of this interstellar interloper eventually brought it on a direct course toward our local neighborhood. By an extraordinary historical coincidence, this object, designated by astronomers as 3I Atlas, hurtled into the inner solar system precisely during a fleeting window of human history. Had this entity arrived a mere 100 years earlier, its passage would have been completely invisible to human eyes, entering and exiting our system without leaving a single trace in our scientific records. Instead, its arrival perfectly intersected with the exact chronological moment where human civilization possessed the technological capability to observe it. Humanity had just deployed an intricate network of advanced terrestrial telescopes, automated wide-field sky surveys, and sophisticated robotic spacecraft operating across various wavelengths of light, allowing us to actively monitor, track, and analyze this unprecedented visitor. This intersection highlights a profound contrast between the macroscopic timeline of the universe and the brief existence of human history. On a cosmic scale, the entire duration of human technological civilization represents nothing more than a fraction of a second. Yet, across this microscopic interval of time, our species managed to develop the tools necessary to intercept the data of an object that has traveled for a period equivalent to nearly 3 times the age of our own planet. To truly grasp the staggering nature of this temporal alignment, let us engage in a classic thought experiment often utilized in advanced astronomical visualization, compressing the entire 13.8 billion-year lifespan of the cosmos into a single 24-hour calendar day. On this monumental cosmic clock, the Big Bang occurs precisely at midnight. For hour after hour, the universe expands in total darkness, slowly forging the first generations of primitive stars and basic galactic frameworks. The interstellar wanderer 3I Atlas begins its epic trek across the freezing void during the quiet pre-dawn hours of this metaphorical day, long before the cosmic clock even reaches noon. Our local solar system does not even begin to condense out of its ancestral gas cloud until late in the afternoon, around 5 o'clock in the evening. The entire evolutionary history of life on Earth, from simple, single-celled organisms to the rise of complex ecosystems, unfurls during the final hours of the night. Where does human technological civilization fall on this scale? Our entire modern history, spanning from the early industrial age to the deployment of space stations, occupies nothing more than a microscopic fraction of a single second just before the final chime of midnight. Yet, it is within this ultimate, imperceptible blink of a cosmic eye that our young species managed to construct a highly sophisticated technological dragnet capable of snagging a traveler that has been flying through the dark since the morning hours. This extraordinary scientific triumph was not a product of mere luck, but the direct culmination of a profound paradigm shift in how humanity monitors the heavens. For centuries, observational astronomy relied on individual scientists manually pointing narrow-field optical telescopes at localized patches of the night sky, a method that would have completely missed a fast-moving, non-periodic interstellar interloper. Over the past few decades, however, space agencies and research institutions systematically built an automated global net of wide-field sky surveys. Utilizing high-resolution digital sensors and automated data pipelines, Systems like the Asteroid Terrestrial Impact Last Alert System actively scan the entire accessible sky every single night. This shift from reactive observation to proactive, continuous surveillance transformed our planet from a blind oasis into an active cosmic sentinel, ensuring that when an ancient relic finally crossed our orbital path, our digital eyes were wide open to capture the definitive data for this groundbreaking space documentary project. This occurrence forces a confrontation with the sheer scale of cosmic geography and the mathematical improbability of such an encounter. We are looking at a literal cosmic time capsule that survived the chaotic dynamics of interstellar space for billions of years, only to reveal its long-held secrets right as our instruments became sophisticated enough to decode them. The scientific data gathered from 3I Atlas introduces an intense layer of intellectual tension that challenges our foundational understanding of celestial architecture. A critical rhetorical question arises among contemporary planetary scientists. Is this object merely a lifeless, ordinary pile of primordial rubble and ice drifting aimlessly through the void? Or does it carry a complex, primal physical code that expands the known laws of celestial mechanics? Initial observations captured erratic structural behaviors, highly symmetrical outgassing patterns, and unprecedented electromagnetic signatures that initially defied simple classification. The presence of anomalous characteristics invites rigorous debate within the international astronomical community, testing the limits of our predictive models regarding how matter behaves when ejected from alien star systems into the vacuum of space. The unfoldment of this historical event serves as an ideal foundation for a sophisticated space documentary, providing an information-rich narrative where every single data point acquired by our space agencies is completely unique and non-replicable. As 3I Atlas begins its final exit past the outer boundaries of our observation networks, the scientific community is left with a monumental repository of information that bridges the gap between our local solar physics and the chemistry of the deep galaxy. This introduction sets the stage for a comprehensive data-driven investigation into the physical properties, isotopic ratios, and gravitational interactions that define this historic interstellar crossing. In late December 2025, the interstellar comet 3I Atlas provided an unprecedented display of celestial activity as it transitioned through the core of our planetary neighborhood. This dramatic phase occurred precisely when the object reached its perigee, marking its closest absolute orbital point to Earth. At a calculated distance of 1.8 astronomical units, which translates to approximately 270 million kilometers from our planet, the comet underwent a sudden and violent transformation. Instruments on board the spectrophotometer for the history of the universe, Epoch of Reionization, and ICE's Explorer mission, a specialized space observatory managed by the National Aeronautics and Space Administration and commonly known as SPHERIX, successfully recorded this massive event. The data revealed that the comet did not merely release a gradual stream of particles, but instead experienced a full-scale volumetric eruption, fracturing its outer layers and ejecting an immense cloud of hidden matter directly into the vacuum. To comprehend the physics driving this late December detonation, planetary scientists analyze the profound impact of thermal inertia within an extreme vacuum environment. 3I Atlas had already passed its perihelion, the absolute closest point to the Sun along its trajectory, earlier in October 2025. Under standard assumptions, the peak of solar radiation should have triggered the highest level of outgassing immediately during that October approach. However, the comet remained surprisingly stable during its closest solar encounter, delaying its major eruptive cycle by nearly 2 full months. This anomaly is elegantly clarified by the thermal mechanics of a structural phenomenon known as the Baked Alaska effect. In culinary terms, this dessert utilizes an outer layer of whipped meringue to insulate a core of frozen ice cream, allowing the exterior to bake while keeping the interior frozen. Structurally, 3I Atlas operates on an identical thermodynamic principle. The exterior of the comet consists of a highly porous dust shell, composed of silicate grains and accumulated debris. This porous outer crust serves as a highly efficient, protective insulating layer that shields the dense, volatile, icy core from the immediate energetic radiation of the sunday. To understand the profound efficiency of this natural insulation, one must examine the specific mechanics of heat transfer within the ultra-high vacuum of interstellar and interplanetary space. In a terrestrial environment, thermal energy disperses rapidly through air pockets via convection and gas conduction. However, within the airless vacuum surrounding 3I Atlas, these classical pathways are completely non-existent. Heat can only penetrate the comet through two remaining modalities: direct solid-to-solid conduction at the microscopic contact points of the silicate grains, and radiative transfer across the empty microscopic pores. Because the outer shell is highly porous and loosely aggregated, the physical surface area where individual dust grains touch is exceptionally minuscule. This creates an incredibly high thermal resistance, severely bottlenecking the inward flow of solar energy. Additionally, the countless empty voids within the crust act as a sequence of miniature radiation shields, scattering and absorbing the incoming solar photons before they can breach the interior. The resulting physical state is a thermal gradient of astonishing extremity. While the exterior dust shell is baked to elevated temperatures by the relentless solar glare, the material just a few meters beneath the surface remains completely undisturbed, locked in a state of deep cryogenic stasis. Consequently, as the comet bypassed its perihelion in October, the intense solar heat did not instantly reach the interior. The thermal energy required a duration of 2 months of continuous, steady conduction to penetrate deeply into the heart of the comet. Once this delayed heat front finally breached the internal boundary, the solid volatile ice within the core underwent rapid sublimation, converting instantaneously from a solid state into massive quantities of pressurized gas. The trapped subsurface pressure quickly exceeded the structural tensile strength of the outer crust, causing the porous dust shell to rupture violently and triggering the powerful, high-velocity jet propulsion systems observed across the solar system. The violent rupture of the outer protective shell allowed space agencies to conduct a detailed, uninhibited investigation into the pristine interior of an interstellar traveler. By isolating and examining the active jet propulsion streams erupting from the core, astronomers utilized advanced spectrometers to break down the chemical composition of the escaping gases. The spectral data exposed a highly complex molecular cocktail containing substantial amounts of methane, methanol, ethane, and formaldehyde. These volatile organic compounds represent the preserved chemical fingerprints of the ancient, distant extrasolar protoplanetary disk, where 3I Atlas originally formed billions of years ago. The precise identification of these specific chemical constituents provides an invaluable window into the physical conditions of a long-dead extrasolar system. In the early phases of star formation, a protoplanetary disk exhibits a stark thermal gradient, where temperatures drop precipitously as a function of radial distance from the central protostar. Volatile compounds like methane, methanol, ethane, and formaldehyde possess exceptionally low condensation temperatures, meaning they can only transition from a gaseous phase into solid molecular ices beyond distinct spatial thresholds, known as chemical snowlines. The abundance of these specific species within the core of 3I Atlas confirms that the object accreted in an ultra-cold, chemically pristine environment, far removed from its primary star's destructive radiation. Furthermore, because these delicate organic compounds are highly sensitive to thermal degradation, their pristine survival over an 11 to 12 billion year odyssey proves that the inner core never encountered significant stellar heating during its long transit through the galactic medium. This remarkable preservation elevates the object from a simple piece of primordial debris into an unparalleled chemical benchmark, allowing this space documentary to present viewers with the raw, unaltered ingredients that primitive planetary systems utilize to build more complex chemical architectures. Alongside these hydrocarbons, the water emissions from the comet exhibited a staggering 40-fold increase compared to its baseline levels prior to the core breach. This massive outgassing rate demonstrated that the internal composition of the object was heavily dominated by volatile ice, which transformed the comet into a highly active chemical factory moving through space. The analytical methodology tracking this discovery represents a flawless logical progression in modern observational astronomy. Initially, researchers were limited to simple optical tracking, watching a raw physical explosion and observing the sheer visual drama of a brightening point of light in the night sky. However, by transitioning from pure physical observation to deep spectral analysis, scientists managed to look past the surface chaos. This systematic, highly detailed breakdown enabled the entire international scientific community to confirm that 3I Atlas was not merely a dry, inert space rock, but rather a functional, primitive hydrocarbon laboratory carrying the preserved raw materials of a completely dead, ancient foreign star system. The precise identification of these chemical ratios allows researchers to compare the basic physical building blocks of our own solar neighborhood with those of ancient stellar systems across the wider Milky Way galaxy, confirming that the fundamental laws of organic chemistry operate universally across interstellar space. As scientists analyzed the structural observations of 3I Atlas, a bizarre geometric pattern emerged from the mapping of the comet's nucleus. By utilizing specialized optical filters designed to subtract the blinding shroud of the glowing gas coma, astronomers successfully isolated the exact positions of the active outgassing channels originating from the hidden surface of the core. The initial data confirmed a prominent, massive jet stream pointing directly toward the Sun, tracking steadily since its early discovery phase. However, the true anomaly was revealed when advanced tracking networks detected 3 additional, smaller mini-jets erupting concurrently from the icy nucleus. Curiously, these 3 secondary outgassing channels were not randomly distributed across the rugged topography of the rock mass. Instead, they were positioned almost exactly 120 degrees apart relative to each other along the localized axis of rotation. This extraordinary geometric precision immediately captured global attention, as such an immaculate arrangement appeared highly unusual for a naturally occurring interstellar object. This geometric discovery triggered an immediate surge in speculative narratives, driving conspiracy theories across media networks and within certain fringe corners of the astronomical community. To many observers, an arrangement of 4 distinct propulsion points, with 3 perfectly balanced at 120 degrees around a central rotational axis, looked far too precise to be the product of random geological formation. Major news outlets quickly capitalized on this structural mystery, publishing reports that questioned whether 3I Atlas was truly an inert piece of cosmic debris. Speculation intensified that this interloper might actually be a sophisticated artificial structure, an ancient interstellar reconnaissance probe, or a manufactured spacecraft actively controlled by an advanced extraterrestrial intelligence. The geometric configuration was frequently compared to engineered propulsion systems, leading many to believe that the symmetrical jets were functional thrusters, stabilizing an alien vessel as it navigated through our solar system, forcing a tense public debate between science fiction concepts and empirical analysis. To resolve the pseudo-scientific tension surrounding this object, planetary scientists look to authentic celestial mechanics, providing a completely natural explanation for these geometric phenomena. The key to decoding the mystery lies in a dramatic behavioral shift observed in the internal rotation rate of the comet following its closest approach to the Sunday. Every comet possesses an intrinsic spin, creating a rhythmic pulsing effect, causing its apparent brightness to fluctuate by nearly 30% as active jets rotate into view. Prior to passing its perihelion, 3I Atlas maintained a stable rotational period of 16.2 hours. However, after enduring the intense thermal energy of the Sun, newer measurements collected in December 2025 revealed that the period had abruptly decreased to a mere 7.1 hours. This meant that the interstellar visitor was suddenly spinning more than twice as fast as its original speed, experiencing a massive acceleration in its localized angular momentum. To appreciate the immense scale of this unexpected mechanical perturbation, one must examine how the unyielding laws of rotational dynamics govern rigid or loosely bound macrostructures within a completely frictionless vacuum. When a celestial object's spin axis undergoes such an abrupt kinetic transition, it signals an immense transfer of kinetic energy that would severely threaten the structural integrity of any standard geological body found within our solar system. In the absolute emptiness of deep space, a spinning object rotates indefinitely without encountering any form of atmospheric drag or tidal dampening, meaning that any profound alteration to its native angular momentum must be driven by exceptionally powerful, internally generated forces acting as a sustained mechanical torque system. This sudden spinning behavior introduces severe internal shear stresses along the celestial body's primary rotational planes, establishing a highly volatile mechanical landscape just beneath the ancient, weathered surface crust. As the localized rotation continually quickens, the physical material properties of this primordial aggregate are forcefully compelled to adapt to a newly established kinetic equilibrium. The linear velocity vectors at the extreme equatorial limbs increase substantially, radically magnifying the structural demands placed upon the core's interior cohesion. For an ancient body with almost negligible self-gravity like 3I Atlas, this swift, high-energy transition from a slow, spinning cryogenic vault into a highly dynamic, accelerating celestial top completely destabilizes the internal pressure matrix, setting the exact structural stage for widespread geological failure. This rapid acceleration is entirely explained by the immense physical torque applied to the nucleus by its newly activated outgassing channels. As internal volatile materials sublimated into pressurized gas, they blasted through the surface crust, acting like natural reaction control system thrusters identical to mechanical jet engines built into human spacesuits and satellites to guide orientation in a vacuum. When these powerful jets fire asymmetrically, they apply a sustained rotational force that rapidly winds up the spin rate of the core. To build a proper physical intuition for this process, one must analyze the structural mechanics of a heterogeneous rock mass spinning at such extreme speeds. Under the influence of an accelerating 7.1-hour rotation, the internal cohesion of the comet is subjected to immense centrifugal forces. As these forces expand, the mechanical stress concentrates along highly predictable mechanical stress arcs, determined by the spherical shape of the nucleus. This structural stress naturally creates perfectly symmetrical geological fault lines and uniform fractures, allowing the pressurized subsurface gas to escape through evenly spaced vents separated by identical angles. To fully understand why this structural stress manifests in such a highly ordered, geometric fashion rather than a chaotic explosion, scientists analyze the fundamental principles of self-organizing natural systems under uniform tension. In materials physics, when a homogeneous or symmetric body experiences isotopic outward stress, the resulting structural fractures naturally propagate along path of least resistance vectors that maximize energy dissipation efficiency. This phenomenon is frequently observed across the natural world, from the hexagonal cooling columns of volcanic basalt on Earth to the highly regular mud cracks formed by uniform drying. On the accelerating nucleus of 3I Atlas, the equatorial stress tensor naturally splits into a triple junction fracture network. This structural behavior occurs because a clean, three-pronged splitting pattern represents the lowest possible energy state required to relieve isotropic rotational stress on a spinning sphere. To clarify this for the audience, we can categorize these physical behaviors into a clear analytical breakdown. An artificial spacecraft relies on variable, computer-controlled thrusters that fire independently to execute complex spatial maneuvers, creating highly irregular, non-symmetrical heat paths. In contrast, a natural outgassing body operates under uniform planetary mechanics, where a spinning sphere under internal pressure will naturally and automatically crack at exactly 120-degree intervals along its weakest equatorial coordinates to achieve kinetic stability. This mechanical realization transforms an apparent cosmic anomaly into an exquisite demonstration of natural self-organization, proving that absolute geometric symmetry is an inherent signature of physics. The integration of these concrete realities allows scientists to effectively debunk the rumors of alien technology, grounding the narrative back into serious scientific reality, demonstrating that the immaculate 120-degree alignment is merely the elegant consequence of structural physics and rotational dynamics, is a fundamental responsibility that any authentic space documentary filmmaker must uphold to maintain educational integrity. By demonstrating how complex cosmic mysteries can be completely resolved through verifiable physics rather than supernatural or extraterrestrial speculation, the true grandeur of natural laws is revealed, transforming a moment of public wild imagination into a profound, information-rich lesson regarding how ancient matter behaves under the intense influence of our local star. On January 22, 2026, an extraordinary geometric alignment occurred within our solar system that provided planetary scientists with an unprecedented observational opportunity. The interstellar comet, designated 3I Atlas, intersected an imaginary straight line drawn directly from the center of our planet to the center of the Sunday. This alignment brought the distant traveler within an incredibly narrow angular deviation of only 0.69 degrees from the exact Earth-Sun orbital axis. To understand the profound physical implications of this positioning, one must analyze the spatial configuration from a structural standpoint. At this precise moment, the Sun was positioned directly behind the Earth relative to the path of the comet, establishing a classic astronomical configuration known as opposition. This alignment initiated a dramatic shift in how light waves interacted with the vast shroud of dust enveloping the nucleus. The resulting visual phenomenon can be conceptually broken down through a precise spatial analogy that illustrates the mechanical properties of light scattering. Under typical conditions, when looking at a comet from a side angle, dust particles within the surrounding coma cast microscopic shadows onto one another. These countless miniature shadows reduce the total amount of light that reflects back toward terrestrial detectors, effectively dimming the object. However, during this unique 0.69-degree opposition event, the light source was positioned directly behind the observer. This precise configuration allowed incoming solar radiation to illuminate the dust halo head-on, effectively eliminating every single micro-shadow within the field of view. To truly conceptualize the profound physical mechanics underlying this opposition effect, we must examine the specific optical behavior of granular material known as coherent backscattering. When observing celestial bodies composed of deeply porous, heterogeneous dust grains scattered across a highly uneven surface, sunlight usually bounces off the outer ridges while casting deep, microscopic chasms of darkness into the craters behind them. However, when the observational viewing angle drops to exactly 0.69 degrees, the incoming light photons travel perfectly parallel to the observer's line of sight. The solar radiation plunges straight down into the deepest, most hidden microscopic crevices of the comet's outer crust and bounces directly back along the exact same optical pathway. Because the observer on Earth is looking squarely down the barrel of the incoming light beam, the shadows cast by the granular structures are completely hidden directly behind the particles themselves. This mechanism momentarily erased the uneven topographical texture of the entire interstellar dust cloud, creating a unified, brilliant sheet of illuminated material. This unique phenomenon is not merely a temporary optical illusion. It is a fundamental property of cosmic light scattering that temporarily forces chaotic, tumbling space debris to perform as a perfectly aligned projection screen. Furthermore, this direct alignment triggered a physical process known as constructive interference. As light waves reflected off the densely packed dust particles, their crests aligned symmetrically, combining their collective energy to create a massive surge in total luminosity. This specific combination of shadow elimination and coherent wave amplification is scientifically defined as the opposition effect. The immediate consequence of this geometric synchronization was a sudden, dramatic 20% increase in the overall brightness of the comet as monitored from Earth. By triaging light paths across these straight coordinates, the universe stripped away the visual noise that usually obscures the structural details of active comets, offering an uninhibited look at the nucleus. This sudden 20% surge in brightness allowed the international scientific community to resolve a long-standing debate regarding the physical scale of the interstellar visitor. Early scientific estimates concerning the true diameter of the solid core were volatile and inconsistent. Because the dense, glowing shroud of the gas coma constantly wrapped around the center, observatories could not easily differentiate between the solid surface and the surrounding atmosphere. This led to widely varying calculations, with initial papers proposing a nucleus radius as small as 320 meters, while other models suggested a structure extending up to 5.6 kilometers. The immaculate geometry of the January alignment permanently settled this mystery. Capitalizing on the sudden elimination of shadows and the bright burst of constructive interference, the Hubble Space Telescope directed its advanced imaging instruments toward the comet to take another measurement. Because the head-on illumination isolated the solid nucleus from the symmetric glow of its surrounding coma, the Space Telescope successfully penetrated the atmospheric barrier. The definitive calculations confirmed that the nucleus of 3I Atlas possesses a radius of exactly 1.3 kilometers. This historic measurement completely eliminated the previous inaccurate upper estimates, ranging from 320 meters to 5.6 kilometers. This incredible scientific precision demonstrates the absolute reliance that modern astrophysics places upon flawless celestial geometry. Without the Earth and the Sun aligning into this perfect mathematical corridor, at the exact moment the interstellar comet raced through our interplanetary zone, our most advanced optical instruments would have remained fundamentally blind to the true structural scale of the object. The dense, glowing hydrocarbon gas would have continued to mask the solid rock, leaving future generations of researchers with nothing but vague estimates and highly speculative data. Instead, the universe provided a fleeting natural magnifying glass crafted entirely out of straight lines, precise orbits, and narrow angles. By capitalizing on this rare backscattering geometry, astronomers successfully peeled away the visual interference, transforming a blurry streak of cosmic light into a clearly defined physical world, measuring exactly 1.3 kilometers in radius. Documenting this specific triumph of orbital mechanics is vital for the narrative progression of this space documentary, as it perfectly illustrates how human observers do not simply passively watch the sky. We actively wait for the immutable, mathematical clockwork of the solar system to grant us momentary windows of profound clarity. The structural investigation of the interstellar visitor designated 3I Atlas represents a historic triumph in global scientific collaboration. When traditional ground-based observatories faced severe visual limitations, an international fleet of robotic explorers executed opportunistic observations across the solar system. These are specialized tracking maneuvers performed by active spacecraft originally assigned to separate missions. By updating internal programming and redirecting sensor arrays, these deep space probes functioned as a synchronized collective. This mobilization allowed humanity to gather unique telemetry data across multiple wavelengths of light, capturing the physical properties and behavioral dynamics of the comet from multiple strategic vantage points. The specialized observations collected during this global initiative are systematically organized into 4 distinct categories of robotic exploration, each managed by different space agencies and technical institutions. The first category involves discoveries made by the X-ray Imaging and Spectroscopy Mission Satellite, a sophisticated orbital laboratory governed by the Japan Aerospace Exploration Agency, or JAXA. In late November 2025, this satellite achieved a breakthrough by detecting a faint X-ray emission signature surrounding the core of the interstellar comet. Prior to this tracking event, every scientific attempt to observe X-ray wavelengths from previous interstellar travelers, specifically Oumuamua and Borisov, ended in failure. The detailed spectroscopy data revealed that 3I Atlas was surrounded by a massive, diffuse cloud of gas interacting with the solar wind. This vast atmospheric halo extended up to 400,000 kilometers from the central nucleus, a scale wide enough to fit every planet in our local solar system side by side. This discovery confirmed that interstellar comets experience charge exchange reactions with solar wind particles in an identical manner to native comets. To precisely decode the profound physics behind this charge exchange process, one must examine the violent subatomic interactions occurring at the absolute boundary of the comet's outer atmosphere. As the ancient celestial traveler plunges toward the inner solar system, it continuously collides with the solar wind, which is a relentless, high-velocity stream of heavily ionized particles expelled by the intense magnetic storms of our Sunday. These incoming solar ions have been aggressively stripped of their native electrons by extreme stellar heat, leaving them with a highly positive, unstable electric charge. When this invisible radioactive gale crashes into the sprawling 400,000-kilometer atmospheric halo of 3I Atlas, the starved solar ions violently interact with the cold, neutral gas molecules of hydrogen and oxygen that are steadily sublimating from the comet's icy core. During these high-speed collisions, the positively charged solar ions actively steal electrons from the neutral cometary atoms to restabilize their own atomic structures. However, these stolen electrons are initially captured in a state of extreme energetic agitation. As the displaced electrons rapidly drop down into lower, stable quantum energy orbits, they must shed their excess kinetic energy by emitting highly specific bursts of electromagnetic radiation. These isolated flashes of high-frequency energy are released directly as X-ray photons. By precisely tuning its specialized quantum sensors to this exact subatomic frequency, the observatory successfully captured this ghostly glowing battlefield, translating invisible electron transfers into a definitive X-ray map. This level of granular atomic observation drastically elevates the standard for any modern space documentary, proving how macroscopic orbital events are entirely governed by the invisible mechanics of quantum physics. The second category features the unique ultraviolet telemetry captured by the Europa Clipper spacecraft, managed by the National Aeronautics and Space Administration, known as NASA. On November 6, 2025, while the automated probe was in its long cruise phase through deep space, its flight mode was temporarily adjusted. Mission engineers programmed the computer to execute 8 hours of continuous ultraviolet imaging of the passing visitor. The resulting spectrographic data provided the first direct molecular confirmation regarding the internal volatiles of the comet. The ultraviolet sensors successfully isolated distinct dust structures and confirmed the presence of hydrogen and oxygen gases. These chemical footprints proved that the sublimation of water ice drove the active comet tail, validating that water remains a fundamental building block across extrasolar systems. The third category comprises the complex navigation camera tracking completed by the Jupiter Icy Moons Explorer spacecraft, which is a major deep space mission governed by the European Space Agency, known as ESA. Operating from a considerable distance of 66 million kilometers, the automated probe utilized its navigation camera system to record 53 consecutive high-resolution images of the moving object. Although this specific camera system was originally engineered to update tracking trajectories on board rather than conduct complex space science, the right timing allowed it to capture a detailed visual log. The data successfully separated the structural architecture of the comet into two distinct features: a highly charged plasma tail composed of fast-moving particles and an extensive, long-duration dust tail. Due to the orientation of the probe, the data experienced a slow transmission rate through a secondary antenna, arriving on Earth in February 2026. The significant operational delay in acquiring these 53 critical images provides a fascinating, behind-the-scenes look into the rigorous logistical challenges and tiered data transmission architectures utilized in deep space networking. The Jupiter Icy Moons Explorer is fundamentally designed to lock its primary high-gain parabolic antenna directly toward Earth to transmit massive volumes of scientific telemetry at optimal speeds. However, executing this unexpected, Opportunistic surveillance maneuver required the spacecraft to physically rotate its entire multi-ton chassis to aim its secondary navigation cameras directly at the swiftly moving interstellar target. Because of this drastic shift in spatial orientation, the main communication dish was forced to face entirely away from our home planet, temporarily severing the high-speed data link. Consequently, the temporary command protocols required the automated probe to safely archive the raw, high-resolution optical data within its secure, onboard solid-state memory banks. To retrieve this trapped information without disrupting the primary flight path, mission control engineers had to delicately route the archived data stream through a much smaller, low-gain secondary antenna system that possessed an exceptionally narrow bandwidth capacity. Sending complex digital image matrices across 66 million kilometers of empty space through a low-gain transmitter operates under strict physical limitations. The digital data packets trickled across the interplanetary void at an agonizingly slow baud rate. This fragmented telemetry drifted through the vacuum in isolated mathematical tiers for months before being successfully captured and chronologically reconstructed by massive radio telescope receiver arrays on Earth. This meticulous, delayed transmission strategy perfectly illustrates the extreme patience and mechanical ingenuity required to execute deep space astrophysics, ensuring that vital visual evidence is carefully extracted from the silent dark. The fourth category encompasses the extensive long-term monitoring executed through the joint efforts of the Parker Solar Probe and the Transiting Exoplanet Survey Satellite, which are managed by NASA and the Massachusetts Institute of Technology, or MIT. The Parker probe tracked the movement of the comet for 18 consecutive days during its 25th solar flyby, providing continuous telemetry data. Concurrently, researchers at MIT analyzed archival data from the TESS system, discovering raw observational signatures recorded as early as May 2025, months before the official discovery of the comet. By combining these overlapping datasets, scientists compiled a series of video sequences that displayed the precise movement of the comet as a bright dot traveling steadily against a background of distant stars. This unprecedented combination of international robotic assets transforms the temporary passage of 3I Atlas into an invaluable, permanent archive of verified interstellar samples. The massive volume of raw data, chemical profiles, and geometric tracking maps generated by these distinct space agencies provides foundational material for many future space documentary projects. By preserving these unique datasets, the scientific community ensures that this historic crossing will remain thoroughly analyzed for decades, illuminating the deep connections between our local planetary physics and the unexplored architecture of foreign star systems. To understand the historical significance of 3I Atlas, planetary scientists evaluate its movement through an astrophysical principle known as the age-velocity dispersion relation. This relationship states that older population objects within the Milky Way travel through space at higher velocities compared to younger stellar bodies. When an object is ejected from its native birthplace, it possesses a modest initial velocity. However, as it travels through interstellar space for billions of years, it encounters massive molecular clouds, star clusters, and fluctuating gravitational fields. Each close encounter acts as a subtle gravitational bump, imparting a tiny kinetic push that gradually increases the total momentum of the body. Consequently, a higher kinetic velocity serves as a proxy for extreme age, reflecting an accumulation of millions of distinct orbital perturbations over a vast timeline. The empirical tracking data gathered from 3I Atlas confirms this kinetic principle. Astronomers clocked the velocity of this interstellar traveler at a speed exceeding 200,000 kilometers per hour. To place this velocity into a comparative framework, this rate is exactly 2.2 times faster than the speed recorded for Oumuamua, which was the first interstellar object discovered passing through our neighborhood. This elevated velocity signaled to deep space observation networks that 3I Atlas was an ancient relic requiring advanced chemical dating techniques to unlock its history. A comprehensive isotope analysis led by scientist Martin Cordner at the National Aeronautics and Space Administration, known as NASA, resolved the mystery of its origin. By utilizing spectrographic instruments to examine the gaseous tail of the comet, researchers measured the structural decay of carbon isotopes within its core. The data determined that the age of 3I Atlas falls between 10 billion and 12 billion years old. This immense age means that the comet was forged a mere 1.8 billion years after the Big Bang, dating back to the primitive infancy of cosmic structure. A profound implication of this discovery is that the star system that originally birthed this comet has exhausted its fuel and died billions of years ago, leaving this wandering ice core as the solitary surviving fossil of a completely erased stellar dynasty. The core insights regarding the birthplace of 3I Atlas were further advanced through a detailed investigation into the atomic composition of the water ice erupting from its fracturing nucleus. Scientific papers released in March 2026 focused on mapping the deuterium enrichment levels of the escaping vapors. Deuterium represents a heavier isotope of hydrogen containing an extra neutron, and measuring the deuterium to hydrogen ratio serves as a chemical fingerprint that identifies the temperature and region where a celestial body was born. The telemetry revealed that the deuterium to hydrogen ratio of 3I Atlas is more than 40 times higher than the baseline levels found in the oceans of Earth. Furthermore, this value is more than 30 times higher than what scientists typically expect to see in native comets originating within our own solar system. Such an extreme concentration of deuterium provides physical proof regarding the environment of its parent system. High levels of deuterium can only accumulate within the coldest, outermost fringes of a primordial protoplanetary disk, where extreme temperatures allow heavy hydrogen isotopes to bond efficiently with oxygen atoms. To construct a proper chemical intuition for this phenomenon, one must understand how temperature gradients dictate the fundamental rules of quantum bonding during the birth of a solar system. At the chaotic center of a spinning protoplanetary cloud, the violent heat emitted by the infant protostar continuously provides enough thermal energy to drive standard hydrogen into chemical reactions, actively suppressing the inclusion of heavy isotopes. However, as one moves billions of kilometers outward toward the freezing periphery of the stellar nursery, the ambient temperature drops well below -250 degrees Celsius. In this hyper-frozen environment, thermal energy becomes incredibly scarce. Because deuterium contains an extra subatomic neutron, it represents a slightly heavier and slower-moving atomic target compared to standard hydrogen. In the near absolute zero of deep space, the sluggish kinetics of deuterium make it far more susceptible to being captured and permanently locked into the molecular crystalline lattice of developing water ice. This strict thermodynamic law means that any planetary body or comet possessing an exorbitant deuterium signature was undeniably constructed at the extreme, frigid outer limits of its native star system, far beyond the reach of any internal stellar warmth. This molecular preservation effectively acts as a frozen vault, keeping the ancient chemistry intact long after the original star collapsed into a white dwarf. By mapping these chemical parameters against the stellar database compiled by the Gaia spacecraft, researchers reconstructed the path of the visitor. The results demonstrate that 3I Atlas originated from a specialized galactic region known as the thick disk of the Milky Way. First identified in 1982, the thick disk represents an extended overdensity of ancient stars that projects far above and below the flatter main galactic plane where our Sun resides. The structural anatomy of the Milky Way is not a uniform, singular disk, but rather a complex, stratified formation built over distinct epochs of cosmic time. The vast majority of standard modern celestial bodies, including our Sun, the Earth, and almost every visible star in the night sky, reside tightly within the thin disk, a highly concentrated band of luminous material spanning the galactic equator. However, encapsulating this central plane is the sprawling ancient architecture of the thick disk. This elevated region represents the original primordial scaffolding of the galaxy, composed of the earliest generations of stars that condensed out of massive hydrogen clouds during the highly turbulent Chaotic infancy of the Milky Way. Objects orbiting within the thick disk possess highly inclined, plunging trajectories, diving aggressively through the galactic plane rather than gliding smoothly along it. The fact that 3I Atlas shares this aggressive, plunging kinetic profile firmly categorizes it as a relic from this foundational epoch, establishing a direct physical link between our modern solar system and the forgotten dawn of galactic formation. The early population stars that populate the thick disk are characterized by low metallicities, meaning they formed when the universe lacked heavy elements like iron or silicon. Because heavy metals were scarce, the elemental composition of these systems was heavily dominated by hydrogen and oxygen, leading to the creation of massive reservoirs of pristine water ice. This low metallicity profile explains why 3I Atlas possessed such a colossal internal reservoir of volatile ice, triggering a spectacular outgassing event as it neared our star. During its peak approach, the comet was expelling material at an astonishing rate of 40 kilograms per second. These precise isotope analyses successfully unlock a pristine chapter in the early history of the universe, delivering the exact type of deep empirical knowledge that dedicated viewers of the space documentary genre always crave to learn. By transforming a distant point of light into a legible geological record, science continues to illuminate the grand timeline of our shared cosmos. On March 16, 2026, the interstellar Voyager designated 3I Atlas entered a highly critical orbital phase that subjected its structural stability to extreme gravitational stress. As the ancient comet continued its high-velocity outward trajectory away from the inner solar system, its path intersected the orbital domain of the largest and most massive planetary body in our entire solar system. The object flew at a calculated distance of approximately 53.6 million kilometers from the absolute core and center of the giant gas planet, which corresponds directly to exactly 0.35 astronomical units. This spatial proximity brought 3I Atlas incredibly close to a dangerous celestial threshold, forcing the weary interstellar visitor to penetrate deep into Jupiter's massive Hill gravitational influence zone. The Hill sphere defines the precise spherical region of space surrounding a planetary body where its own localized gravitational pull exerts a dominant control over moving objects, completely overpowering the immense background gravitational attraction of the Sunday. This swift encounter initiated a monumental physical tug-of-war between the immense mass of the gas giant and the extraordinary momentum of the interstellar interloper. Given the colossal size of Jupiter, which possesses a mass over 300 times greater than Earth, many public observers and amateur astronomers questioned why the planet could not successfully capture this passing object, bringing it into a permanent orbit as a new long-duration satellite. The definitive scientific resolution to this inquiry is rooted firmly in the unyielding foundational law of conservation of energy and the strict mathematical parameters governing escape velocity. For any celestial body to successfully capture an incoming object into a stable, closed elliptical orbit, the total mechanical energy of that incoming object relative to the host planet must be negative. This means the planet must exert enough gravitational force to slow down or break the approaching body, stripping away its excess kinetic energy until its speed drops below the localized escape velocity of the system. However, the primordial kinetic energy possessed by the traveler 3I Atlas was far too immense for such a capturing mechanism to occur. Having spent billions of years accelerating across the galactic void, the comet entered our solar system moving at an exceptional hyperbolic velocity. Even when traveling deep within the densest pocket of the gas giant's Hill sphere, the kinetic energy of the visitor vastly exceeded the gravitational potential energy available to bind it. To make this abstract concept of energy dynamics intuitively clear, we can utilize a mental visualization centered around the physics of a simple gravitational valley. Imagine the massive gravitational well of Jupiter as a steep, incredibly deep physical crater. If a slowly moving asteroid rolls over the edge, it will spiral downward, losing momentum to the slopes until it becomes permanently trapped, circling the bottom. However, 3I Atlas approached this gravitational crater carrying what astrophysicists define as an extreme hyperbolic excess velocity. When the ancient comet plunged into the Jupiter well, it accelerated drastically toward the center, but its immense positive kinetic energy acted as a massive protective shield. It essentially dove straight into the deepest part of the crater and possessed more than enough residual momentum to race directly up the opposite slope and launch itself back out into open space. In the strict framework of the vis-viva orbital equation, because the total mechanical energy of the comet remained a strictly positive integer, its mathematical path through space was locked into an open hyperbolic curve rather than a closed ellipse. Unless a sudden massive atmospheric drag or a catastrophic collision with one of Jupiter's moons occurred to forcefully strip away that excess kinetic energy, the fundamental laws of thermodynamics absolutely guaranteed that the interloper would escape the trap and continue its relentless journey through the dark. Consequently, Jupiter's tremendous gravitational pull was simply not powerful enough to act as a mechanical brake. Instead of forcing the fast-moving comet into an enclosed orbit, the planet could only apply a brief, highly localized directional acceleration. This immense planetary gravitational tug was only capable of deflecting the velocity of 3-1 Atlas by a minor margin of a few meters per second. This slight structural deflection, though seemingly minor on a local planetary scale, was completely sufficient to derail the long-term path of the traveler. This precise deflection is a natural manifestation of the gravitational slingshot effect, fundamentally altering the comet's absolute trajectory relative to the center of the Milky Way. When 3I Atlas passed behind the trailing hemisphere of the gas giant, the immense gravity dragged briefly against the comet's forward momentum, forcing a minute deceleration relative to the Sunday. However, this interaction did not just change speed, it warped the absolute geometry of the escape vector. By shifting the outgoing angle by merely a fraction of a degree, the interaction magnified an invisible geometric wedge that will expand infinitely as the comet travels deeper into the galactic void. Millions of years from now, this tiny localized planetary bump will cause the object to cross paths with entirely different molecular clouds and alien star clusters than it originally would have encountered. It is a stunning display of cosmic cause and effect, where a brief orbital handshake lasting only a few hours fundamentally rewrites the destination of a 12-billion-year-old traveler. This rigorous breakdown of orbital dynamics ensures that this space documentary avoids framing the encounter as a near-miss catastrophe, but rather correctly identifies it as a profound, mathematically precise transfer of spatial geometry between two celestial titans navigating the dark. By permanently altering its exit velocity vectors, the gravitational assistance of the gas giant reshaped a journey that spans billions of years, bending its departure line as it prepares for its ultimate escape into interstellar space. The precise telemetry data recorded during this historic crossing provides an exceptional case study for a space documentary demonstrating how the complex architectural layout of our solar system actively interacts with these pristine remnants of the deep galaxy, permanently casting them back out into the dark interstellar void to wander alone. The temporary passage of the interstellar Voyager designated 3I Atlas leaves behind a profound, permanent lesson regarding celestial humility and the limitations of terrestrial exploration. The extensive tracking data gathered across multiple light wavelengths has forced a stark realization within the international scientific community that human technology has only observed the mere tip of a colossal cosmic iceberg. This stark realization redefines our relationship with the unknown cosmos. Recent mathematical modeling and astronomical calculations show that hundreds of independent interstellar objects are currently passing undetected through our local planetary system at any given moment. Yet, because our present automated sky surveys lack sufficient depth and resolution, humanity remains completely blind to their presence, letting these ancient, unmapped wanderers slip silently through the local void without a single signature being recorded by our defense sensors. The departure of 3I Atlas back into the absolute darkness of the galactic medium has successfully spurred humanity toward building more advanced, sensitive deep space observation networks. Foremost among these collaborative international projects is the rapid completion of the Vera C, Rubin Observatory, located in Chile, designed with an exceptional wide field reflecting telescope capable of surveying the entire available night sky every few nights. By capturing these dim targets, we will systematically catalog the galactic debris field. This technological facility will eliminate our historical operational blindness, actively scanning the outer orbital boundaries to prepare our planetary tracking networks for the arrival of the next inevitable interstellar visitor, which will be officially designated as 4I. As this ancient traveler recedes beyond our detection instruments, it forces a permanent re-evaluation of our planetary isolation. This conceptual intersection serves as the definitive hallmark of a profound space documentary, bridging raw astrophysical telemetry with a deeper philosophical inquiry into our actual position within the vast celestial web. If our local system is constantly populated by unmapped fragments born from foreign star systems that died billions of years ago, we must question our traditional understanding of Earth's coordinates. This enduring question will challenge our space exploration priorities for generations to come. Are we truly isolated observers, living on a lonely oasis of rock? Or is our home planet drifting through a crowded interstellar highway where the remnants of ancient worlds constantly brush past us in the silent dark? To dwell upon that profound question is to fundamentally accept the transient nature of all galactic civilizations, including our own. The silent retreat of 3I Atlas provides a chilling yet beautiful reflection on the ultimate fate of solar systems. Billions of years from now, long after our own sun has exhausted its nuclear furnace and violently expanded into a red giant, the Earth and the surrounding terrestrial planets will be completely incinerated. However, the outer icy remnants of our Oort cloud will be violently scattered into the deep interstellar medium. The frozen fragments of our own dying neighborhood will become the new wandering ghosts of the Milky Way, drifting for eons through the pitch-black void. Perhaps tens of billions of years in the distant future, a fragment of our own solar system will briefly cross the path of another young, curious alien civilization. Their scientists will point their own automated telescopes toward the sky, marveling at the chemical fingerprints of our long-dead world, entirely unaware that the icy rock they are observing once orbited a star that nurtured human history. This cyclical cosmic reality transforms the study of astronomy from a mere collection of raw data points into a powerful mirror, showing humanity not just where we came from, but exactly what we are destined to become. Thank you so very much for watching this complete scientific breakdown of 3I Atlas. The historical trajectory of this ancient interstellar traveler reminds us that our local solar system is not a closed sanctuary, but an active participant in a much grander galactic narrative. By analyzing the unique telemetry data gathered from multiple robotic missions, our global scientific community continues to piece together the primitive chemical signatures of alien star systems that flourished billions of years ago. We owe a major debt of gratitude to the dedicated space agencies and international research networks whose collaborative efforts captured these non-replicable milestones before the visitor vanished into the dark void forever. If you found this rigorous exploration of celestial mechanics and elemental isotopes deeply engaging, please consider subscribing to this educational astronomy channel and leaving your analytical thoughts in the comments section below. Your active interaction provides the vital fuel that allows us to produce serious, data-driven content for dedicated space enthusiasts worldwide. We will continue to scan the deep sky, monitoring the outermost boundaries of our local neighborhood for the next inevitable wanderer. The universe contains an infinite repository of unmapped anomalies, and we look forward to unraveling the next great cosmic mystery alongside you during our upcoming astronomical broadcasts. Until our paths intersect once more across these straight coordinates, keep looking up toward the beautiful distant stars, stay perpetually curious about the eternal laws of physics, and thank you once again for your incredible time, attention, and sustained support.